Powerball is a multi-state lottery. The following probability distribution represents the cash prizes of Powerball with the corresponding probabilities. So we have three parts to this question. If the jackpot is $20 million, find and interpret the expected cash prize. If a ticket costs $2, what is your expected profit from one ticket? B, to the nearest million, how much should the jackpot be so that you can expect a profit? Assume nobody else wins so that you do not have to split the jackpot. And C, does the size of the jackpot affect your chance of winning? So let's take a look at this distribution. Earlier in the semester, we looked at Mega Millions. Actually, it was just back in chapter 5, and we calculated the probability of winning the Mega Millions jackpot. Well, Powerball is similar to Mega Millions. They're not the exact same, but they're set up in similar kind of structures. The games are similar. They just have different numbers of balls, but otherwise they kind of structured the same way. So what we have here is the possibilities of what's going to happen if you purchase a Powerball ticket. You might win the jackpot. You might win $1 million. You might win $50,000, $100, $7, $4, or $0. So these are the possible outcomes. Now the probability of winning the jackpot you can see here, pretty slim. The probability of winning $1 million you can see here, pretty slim. The probability of winning $50,000, pretty slim. $100, pretty slim. $7 is even pretty slim. $4 is pretty slim. The probability of winning $0, not so slim. So this probability is much higher. If you buy a Powerball ticket, much more likely to win nothing than the other stuff. Now, the jackpot changes from drawing to drawing, depending on if someone has won. So the minimum jackpot that can be awarded is $20 million. So the way it works is once somebody wins the jackpot, then the next drawing, the jackpot is set at $20 million. And then from there, as the game is played and nobody wins, the jackpot grows. Again, just like Mega Millions. So that's why I use 20 million right here. That's the minimum jackpot. So if the jackpot's 20 million, we want to find and interpret the expected cash prize. So here for jackpot, I'm going to write 20 million. That's my value. Whoops, I have that off camera. So 20 million is going to be my jackpot. So using that 20 million jackpot, I want to calculate the expected cash prize. Well, so in other words, I want to find the mean for this probability distribution. Now, before I do this, I do want to point out that the value of the expected cash prize is going to change depending on the jackpot. So if the jackpot's $20 million, I will have one value for the expected cash prize. If the jackpot is $30 million, I will get a different value for the expected cash prize, and so on. So the expected cash prize is going to change from drawing to drawing to drawing, depending on what the jackpot is for that drawing. So essentially all I need to do is find the mean. So I'm going to take each outcome, each cash prize, times the probability of winning that cash prize. So here I'm going to take my 20 million times this probability. Let me bring my calculator in and I'll do that real quick. So 20 million times the probability of winning the jackpot, which is 0.00000003422. And so that is 0.06844. Now, again, that value is what the value is if the jackpot's 20 million. That value right there would differ if the jackpot's not 20 million, if it's something else. Now, I'm going to take 1 million times this probability. Now, you can use your calculator if you want, but when you multiply by 1,000,000, all that's really going to happen is the decimal point's going to move to the right 6 places. So if I move the decimal point to the right 6 places, that's going to be 0.0855557. 50,000 times this probability. So 0.000001095,134. And so that is 0.0547567. 0.0547567. When I take 100 times this probability, multiplying by 100, the decimal point's going to just move 2 places to the right. So that would be 0.00963,72574. Seven times 0.03150671455. That is 0.02205470002. 4 times this probability. So 4 times 0.037185354,691. And so that is 0.1487414,188. And last but not least, if I take 0 times this probability, that will be 0. So if I want to find the mean of this random variable, the mean, again, for the cash prize is going to be what I get when I add that up. So I'm going to write that up here. So if I add this up, 0.06844 plus 0.085557 plus 0.0547567 plus 0.00963,72574 plus 0.02205470002 plus 0.1487414,188 plus 0. That equals 0.3891870764. Now that's talking about a cash prize, so that's talking about money. So if I round that to the nearest penny, we're really talking about 39 cents approximately. So if the jackpot for Powerball is $20 million, for every ticket that's sold, every ticket that's purchased by a player, on average, the player can expect to win 39 cents. The trouble with that is that a ticket costs $2. So if you spend $2 for the ticket and can expect to win 39 cents in return, that is not a fair game. So what is your expected profit? Well, your expected profit will be the difference between what you expect to win and what you paid. So if I take the 39 cents and if I subtract the $2, that's going to be a negative $1.61. So really what's happening, particularly from the perspective of the lottery, if the jackpot's $20 million, the lottery is going to make, on average, about $1.61 per ticket sold. The players, on average, are going to lose $1.61 per ticket sold. Again, if the jackpot is $20 million. It would be different if the jackpot's a different amount. So B, to the nearest million, how much should the jackpot be so that you can expect a profit? Assume nobody else wins so that you do not have to split the jackpot. So the question then is, if this is the expected profit, if the jackpot's $20 million, then what would the jackpot have to be so that your expected profit could actually be a profit rather than a loss? In other words, what would the jackpot need to be so that the lottery, that the Powerball is fair? So the way I'm going to figure this out is I'm going to let X represent the jackpot. Now, if X represents the jackpot, then instead of getting this value right here, I would get this probability times whatever X is. And I'm going to write that down here. So I would get 0.00000003422 times X. So that would be the value that occurs right here. Now, all of these other values that I get right here would not change. The million doesn't change. The 50,000 doesn't change. None of these other values change. So these probabilities don't change. These values would all stay the same. So if I add up these other values here, I'm going to put that right here. So 0.085557 plus 0.0547567, and so on. That's 0.3207470764. So again, if the jackpot is X, then my expected winnings would be this, 0.00000003422 times X plus 0.3207470764. So that would be my expected winnings. And I want that expected winnings to be greater than $2 in order for me to expect a profit. Now I'm setting it greater than $2 because that's what the cost of the ticket is. So again, if I want to have an expected profit, then my expected winnings has to be greater than the cost of the ticket. That's the idea. So that's just a linear inequality that I can solve. So I'm going to subtract this 0.320747074 from both sides. And if I do that, I'm going to get 0.00000003422x, and that's going to be greater than 2 minus that. Well, if I take 2 minus that amount there, then that's going to be 1.679252924. And so if I solve for X, I can divide both sides by the coefficient here. So X is going to be greater than this divided by the 0.0000000003422. So divide by 0.00000003422, and that gives me this value, 490,722,654.5. So if the jackpot is greater than $490,722,654.50, then I would expect a profit. My expected winnings would be greater than the cost of the ticket. Now, this said to the nearest million. So if I round that to the nearest million, that would be about 491 million. So rounding up, then I actually would make a profit. And by the way, I do think the lotteries generally do round to the nearest million. So they wouldn't have a jackpot this precise as a general rule. They normally round that off to the nearest million. So as long as the jackpot is 491 million or higher, then the expected profit would be actually a profit rather than a loss. But if the jackpot is less than 491 million, then the expected profit really isn't a profit at all. It would be a loss. Question C. Does the size of the jackpot affect your chance of winning? Explain. So if the jackpot's 491 million, does that make it more likely that you're going to win it? No. Your probability is not going to change. The only thing that really changes is, again, the expected value. So don't confuse that. Just because the expected value goes up, that doesn't mean you're more likely to win, and you're not less likely to win. So all that means is that it's now a fair game. You're still probably going to lose if you buy a lottery ticket, right? You're still probably going to lose, but at least if it's this high, the game is more fair to the player than if it's down to 20 million. So the answer to C, does the size of the jackpot affect your chances of winning? The answer to that is no. And the reason is because the probabilities of winning the different amounts do not change. So regardless of what the jackpot is, the probabilities stay the same.